Hey, so I know a few people have been having some questions about Riemann sums and the angle approximation. So I wanted to give you all an alternative to the assignment that's on eClass right now that is a little bit more in line with how you guys will see this on the exam. So I've set up some things already because the setup can be a little complicated. But we're looking at the function y equals negative x squared plus 4x plus 1. So that's this graph right here. Now, we want to divide this into 4 subintervals from 0 to 4. So what we have to do is we take the two ends of our interval, so 0 and 4, and subtract, and then divide by how many subintervals we want. And that tells us how big each of our subintervals is. So as you can see, I took each of our intervals or subintervals and made each one 1 unit wide. Now, we're working on left rectangle approximation in this example. So what that means is we're going to draw a bunch of rectangles that the left side of the rectangle touches the graph. So the left side of the first rectangle touches the graph, the left side of the second one, the left side of the third one, and the left side of the fourth one. Now, I was using a highlighter, so forgive me a little bit if it's not quite accurate. But now we need to find, because we're doing area approximations, we're getting an approximate area under this curve by estimating using these rectangles. Okay, so my first rectangle, you see, doesn't, like, there's a lot of space between the top of this rectangle and the graph up here, because it has to touch over here on the left. As you can see over here, there's a bunch of rectangle outside the graph because, again, we want our left side to touch. So when we figure out the heights of these rectangles, we're using the left side of the rectangle. So I kind of laid that out down here. We want the area of each rectangle. So the area, of course, is base times height. The base of each rectangle is 1 unit. Now the height of the rectangles is what changes. The height of this rectangle is whatever the function is equal to right there. So this is 0. So this would be 1 times f of 0. This one, the base is 1. The height up here is whatever the height of the function is at x equals 1. All right, and then so for the third rectangle, we're going to go all the way up here to the top. And this one, the height of this rectangle is equal to whatever the function is right there. So that's at 2. So that would be f of 2. And then the fourth rectangle, the height of that fourth rectangle is equivalent to whatever the point is right here, where x is 3. Okay, so now to figure out the heights of those rectangles, we have to substitute 0, 1, 2, 3. So we're using these points, these x coordinates, to figure out the heights of our rectangles. Notice the last coordinate, the end of our interval, does not get used because we're looking at all the left side points. So this would be 1 times f of 0 is just going to be 1. Just remember our function is negative x squared plus 4x plus 1. So this would be 1 times negative 1 plus 4 is, or I'm sorry, yeah, negative 1 plus 4 would be positive 3 plus 1 is 4. F of 2, so that would be negative 4 plus 8 is positive 4 plus 1 is 5. And then f of 3 would be negative 9 plus 12 is positive 3 plus 1 is 4. Okay, so the area of our first rectangle is going to be 1 unit, and that makes sense because it's 1 wide and 1 tall, so 1 times 1. So I'm going to put that in there. A2 would be 4, and that makes sense because it's 4 units high, 1 unit wide. A3 would be 5. That makes sense again. It's 1 unit wide and 5 tall. And then A4 is going to be 4 again, and you can see they're about the same height. Okay, so now if we wanted to find the entire approximate area, we would just add them up. 1 plus 4 plus 5 plus 4. So this would be 10. So our left rectangle approximation of the area underneath this curve from 0 to 4 is 14, an approximation. Okay, so how would that differ in a right rectangle approximation? So I have the same setup, same number of intervals, except now if you look, my 2 graphs are kind of the opposite of each other. My rectangles are like mirror images of each other, because this time we're using the right side of each rectangle. So again, the right side tells me I want to know how tall the rectangle is at this point. I want to know how tall it is at this point, how tall it is here, and how tall it is here. So we want to know what f of 1 is to calculate this first area. We want to know what f of 2 is to calculate the second area. We want to know what f of 3 is to calculate the third area. And we want to know what f of 4 is to calculate the fourth area. So notice we've used 1, 2, 3, and 4. In this case, the beginning of our interval, or 0, has not been used. All right, so we did some of these calculations before. I know f of 1 equals 4, f of 2 is 5, f of 3 is 4, and f of 4 would be negative 16 plus 16 is 0, so f of 4 would be 1. We add those all together to find our area. I added them backwards, sorry. And we get, again, that our right rectangle approximation is 14 as well. Okay? All right, so now we want to look at the midpoint approximation. So the midpoint means that it's the middle of the interval that touches the function. So here, from 0 to 1, I want what's in the middle. So that's going to be 1/2. So that's my x-coordinate 1/2. That's the middle. Here I want the middle between 1 and 2. So that's right here. So the middle between 1 and 2 would be 3/2. Here I've got the middle between 2 and 3. The middle between 2 and 3 would be 5/2. And then the middle between 3 and 4 would be 7/2. Now, if you notice, we're actually not going to use any of the endpoints on the interval. We don't use the beginning endpoint, we don't use the middle, we don't use any of the interval endpoints either, because what we want to look at is in the middle of each one. Now, this is a lot of calculation to do. Okay, so everything is 1 times, so 1 times f of 1/2, 1 times f of 3/2, 1 times f of 5/2, and 1 times f of 7/2. Okay, through the magic of technology, I did all of those calculations. So when you put in 1/2, you get 2.75 out for the area. When you put in 3/2 or 1.5, you get 4.75. For 5 halves, we also get 4.75. And then for 7 halves, we also get 2.75. And if we look at our drawing, that looks like it's right. The two end intervals look to be the same height. The two middle intervals are the same height. So what I got for area seems to make sense, that the two outer ones would be the same and the two inner ones would be the same. So now we just want to add those together. Okay, so we are going to do 2.75 plus 4.75. And since we've got two of those, we're going to multiply by 2. And for this approximation, we get about 15, so a little bit more. So this is our midpoint approximation. Now, for your exam, you really need to pay attention to the intervals, what points you're using to make your calculations. We could very easily have turned this into a table. Let me go back and look at one of the other ones. We very easily could have turned this into a table and said, okay, what x am I using? What f of x? And then what's the area? Oh, we want our interval as well, or n. So for each one, the interval is 1. For the first one, our x coordinate that we used was 0, so we would use f of 0. Our second one was 1, so we would have used f of 1. And 3, we would have used f of 3. And then we would take whatever we get for these two and multiply. Understanding though, if you were doing a midpoint, you'd want to use the points in between. And then f of 4 didn't get used at all. If you were doing a midpoint, you'd want to use the points in between. If you were doing a right rectangle approximation, you wouldn't use the first one. So what you really need to pay attention to is which points are being used to calculate your areas. Okay, I hope this was helpful. I do have an assignment for you to work on that will be, not only will it be review, but if you didn't do some of the Riemann sums assignments, this will make up for it. Hope this helps.